Hello, everybody. While Tim gets set up, just want to say thanks, everyone, for coming to the GPU Mini. We're going to have several exciting talks today and then end on a panel discussion. So, oh my goodness, OK, I'm hearing my own voice. Please stick around for that. And take it away, Tim, Julia Hub, GPU Impresario.
Thank you. Thanks for attending. So today I'm going to be talking about OpenCL.jl, which is a new GPU backend that I've been working on for the past year, and how we revived that to run GPU code on the CPU. So bunch to unpack. Before that, I'll start with some motivation for this whole effort. And the motivation for this work starts with kernel abstractions, which I'm assuming many of you will be familiar with. So kernel abstractions, you can see on the left-hand side, there's a bit of code that uses CUDA.jl to allocate some data and launch a very simple vector addition kernel. On the right-hand side, you have the equivalent using kernel abstractions, and you can see that only the kernel definition and the kernel launched have been substituted with something that's vendor neutral. And we do that by using macros. And using these macros, we can target a bunch of GPU backends. And that's fairly straightforward because all GPU backends, whether you're using them from Julia or from the vendor-specific languages, they use a SPMD abstraction for kernels. SPMD is single program multiple data, as opposed to SIMD or MIMD. It basically means that you write a single piece of code that's going to be executed across a whole bunch of data. And the code differentiates what it executes by using certain intrinsics, like here, the @index intrinsics we define in kernel abstractions to figure out which work item this instantiation of the thread has to work on. And all of our GPU backends take this kind of kernel language as input, which means that the conversion from the kernel abstractions definition to the vendor-specific one is very straightforward. For the CPU, that's not the case, because GPU kernels often are launched over tens of thousands of threads, so we cannot simply use one CPU thread for every GPU thread, meaning we have to do parallel code generation. And for example, for a simple reversal kernel, which will reverse the elements of an array, that basically boils down to generating loop nests, processing multiple work items of each block in a row, and then in between the loop nests, you have implicit synchronization because the one loop nest finishes and then the other loop nest starts again. So that may seem like a fairly straightforward mapping. The problem is that SPMD kernels do not cleanly map onto loop nests. And as a result, we have quite some issues with this mapping. One, for example, is the issue of scope. Things that are defined within the for loop that we generate are not visible outside of the for loop. So that's a clear violation to what the kernel was originally written as. You might wonder at this point, why do we even have a CPU backend at all? Because kernel abstractions is a GPU programming abstraction library. And it is, that's true, but originally we added a CPU backend to facilitate debugging so that you can at least run the GPU code on the CPU, add some print statements, and so on. Nowadays, now that kernel abstraction is becoming a little more popular and more Julia libraries are being written using kernel abstractions, the CPU backend is also becoming more important in order to ship code to people that do not have a GPU, because you cannot assume that everybody has a GPU in their laptop. One example of that is, of course, continuous integration services. It's fairly hard to get a CI service that has a GPU. So if you want to test your library, it's good that we support a CPU backend at least. And finally, it would also be great if we could use the CPU backend to extract some more performance from your system, because ultimately it's silly if those powerful CPUs aren't doing nothing while you have the GPUs computing. So basically, that's just a bunch of motivation why it is interesting to have a CPU backend. But as I explained before, the whole mapping from these SPMD kernels to parallel CPU code that uses for loops is tricky at best. And it also has some implications on the kernel abstractions API. For example, to get by the scoping issue I mentioned, Kernel abstractions has this add uniform macro, which tells the system that a certain abstraction, a certain expression can be hoisted out of the for loop and its side effects can be visible for the entire work group. The counterpart of that is the add private macro, which makes sure that something is only visible for the current work item. In principle, this shouldn't be necessary because the SPMD kernel is fine by itself. It's only the mapping to for loops that complicates and introduces this whole scoping issue. And there's a bunch of other issues. For example, it does not support early returning from an arbitrary point in the kernel. It limits the how you have to use the kernel abstractions primitive functions, which has to be in an add kernel function. It also requires the synchronization to happen at top level and so on and so forth. So the bottom line here is that the CPU backend has quite some issues, and those issues aren't limited to the CPU backend itself, but they also have an impact on the kernel abstractions API as a whole. So the conclusion basically here is that we need a new CPU backend that works, and as a result, hopefully can unleash the kernel abstractions API. And that's when we discovered PoCL. PoCL is a portable open computing language, which basically is an implementation of OpenCL. So OpenCL is an API that's being used to execute compute programs on the GPU, but it's just the API. You have a driver implementing this API, and PoCL is one of these drivers. And as you can see at the bottom, PoCL supports a whole bunch of backends, and one of those backends is a CPU backend, meaning they do all of the complicated mapping and compilation of SPMD inputs to parallel loops in order to execute it on the CPU, so we can piggyback on them. Especially so because it's OpenCL, and we already have OpenCL.jl. And with OpenCL, you can feed SPIR-V kernels into the system, and we have GPU compiler to compile Julia code to SPIR-V. So in principle, we can simply use OpenCL. Sadly, things aren't that nice. OpenCL.jl turns out was pretty old and unmaintained. You can see the contributor chart on the right. It was one of the earliest packages that existed in Julia, earliest GPU programming packages, but nowadays it was desperately in need of a maintainer. So that's what I've been working on for a handful of months, the past couple of years, reviving OpenCL.jl such that we can use it to target the CPU backend of PoCL and unleash kernel abstractions. So as I mentioned, OpenCL was one of the first GPU programming packages that we had in Julia, which as a result also influences how you program a GPU with it. So here on the left-hand side, again, I'm rolling with vector addition as a very simple, understandable example. You can see how, first of all, the kernel code has to be written in OpenCL-C. So back at that time, there wasn't GPUCompiler, so there wasn't a way to compile Julia code for GPUs. So you had to write your kernels in C. We then allocate some data on the CPU, but before uploading it to the GPU, you had to manually manage your state. That is, which device to execute on, a compute context, a command queue. You had to instantiate all of that manually. After that, you had to use lower level APIs to compile your kernel, and finally upload the data to the GPU using a buffer, which is not an array, so no full-fledged array abstraction. And then finally launch the kernel with slightly clunky syntax. So this is very different from what our modern GPU backends look. And as a result, integrating the current state of OpenCL.jl into code that assumes the GPU backend, such as the other GPU backends, is not going to work well. So OpenCL.jl integrates fairly badly with the rest of the GPU ecosystem. So first of all, we modernized the package by, for example, getting rid of the explicit global state, switching to an array abstraction. So now we have the CL array abstraction instead of CL.buffer, and switching to a much more CCall-like calling function CL call instead of punning on the getIndex function on a kernel object. So that was the first step, modernizing the APIs, making sure you don't have to use low-level stuff. And next up, we integrated with GPU Compiler in order to support compiling Julia code straight up to SPIR-V code, which we can then feed to the driver. And now this is the current state of OpenCL.jl, which is extremely similar to all of our other backends. You define a kernel function just as any ordinary Julia function, and you launch it using a macro here at OpenCL, which is very similar to at CUDA. So OpenCL.jl now already is a very potent GPU backend you can use. Behind the scenes, that required a significant amount of work. So there was obviously the integration with GPU compiler in order to generate SPIR-V code. The array abstraction implements the entire GPUArrays interface, so we can reuse all of that functionality that we already have implemented in GPUArrays. We obviously provide a kernel abstractions backend. In order for this code to compile, we also had to support more modern versions of OpenCL, as well as detect which extensions your driver supports in order to be able to derive a pointer, because generally in OpenCL, you work with opaque buffers and handles to it, not with device pointers, which is tricky because an array in Julia is a struct containing a pointer. So having to work with that required exploring and detecting which extensions your device supports and accurately selecting one or another. And finally, we also use JLLs to package up as much of the OpenCL ecosystem as we can, namely the loader, because again, OpenCL is plugin driven with a bunch of drivers that can registrate, and the drivers itself being PoCL. And as an example of that, here I'm showing how on the current version of OpenCL, you can import the package, OpenCL, you can import a driver, PoCL, for example. And then when you perform the first API call, the OpenCL ICD loader will detect all available drivers, both drivers that are activated through a JLL, which will register themselves automatically with the driver loader, as well as any system drivers available on your system. For example, here, this is on my workstation. I run OpenCL.version.info, and it obviously reports the PoCL driver, which has been imported through a JLL, but also my system drivers, such as the Intel one and the NVIDIA one. The next step is taking all of that functionality and integrating that in kernel abstractions. And this is still a work in progress, so it's not released yet, but in the next version of kernel abstractions, you will be able to use the PoCL backend, which will be an integrated backend, and you will be able to take any kernel abstractions kernel function and execute that on the CPU using the PoCL backend. It's a very lightweight way of doing things. We don't actually depend on the entirety of OpenCL.jl. We just integrated whatever we needed, as well as PoCL, into kernel abstractions. Yet we now support the entirety of kernel abstractions. So because of relying on PoCL's SPIR-V to CPU compiler, we don't have to do the manual mapping of kernels to for loops anymore. It also directly uses Julia arrays, so it's very convenient. You don't have to use a separate array type. There is one disadvantage, namely that this because we now go through GPU compiler, the kernel code is now also having to stick by the subset of Julia that GPU compiler uses. So you cannot do dynamic invocations anymore. You cannot trigger the garbage collector anymore. This was something that was possible with the old CPU backend. The new CPU backend has to stick by the rules of the other GPU backends. But to some extent, that's a good thing because you can develop code, you can test it on CI, and if it works on CI, you know that it will work on the other GPU backends as well. So disadvantage, that may be an advantage as well. So that was how we can use PoCL through OpenCL to enable a CPU backend and kernel abstractions. But OpenCL.jl itself can do quite a bit more for us. So again, the current state of affairs out of the box is that you can use OpenCL.jl to, for example, program your Intel GPU, because the Intel GPU supports SPIR-V. You can also use it with NVIDIA GPUs, but I use the dotted line because the NVIDIA OpenCL driver does not support SPIR-V. So you'll have to use kernels written in OpenCL-C, and if you're using the NVIDIA GPU through OpenCL, you will not be able to compile Julia code to OpenCL code for your NVIDIA GPU. That doesn't really matter because we, of course, have CUDA.jl, which should be the preferred package to work with NVIDIA GPUs. But it is possible to use an NVIDIA GPU through OpenCL.jl. Then there's, of course, also PoCL, which has a CPU backend. But if you remember the initial overview I showed of the PoCL architecture, it also supported a bunch of other backends. So we can actually use the NVIDIA GPU through PoCL, and that does support SPIR-V to OpenCL compilation. So through PoCL, it's not part of the released JLL yet, but if anybody would be interested in it, it's actually possible to use the NVIDIA GPU and a bunch of other GPUs through OpenCL.jl by using PoCL. We're also investigating some other possible routes of using backends such as NVIDIA's, which only supports OpenCL-C, and that is by using the SPIR-V to CL binary. SPIR-V to CL is a project that aims to cross-compile SPIR-V code back to OpenCL-C. And again, for the NVIDIA driver, that's not particularly relevant, but this may be relevant for embedded GPUs because there's many embedded devices which have an OpenCL driver, but that OpenCL driver only supports OpenCL input. So with this, it may be possible to extend the reach of the JuliaGPU ecosystem to all of these embedded devices that support OpenCL. There's other interesting drivers. For example, there's Rustical. Rustical is an OpenCL implementation that's open source and is part of the Mesa open source graphics library. Rustical is an OpenCL driver and it runs on Gallium drivers. Gallium drivers are the drivers that are internal to the Mesa project. And one of those drivers is Zinc. Zinc is an interesting driver because it cross-compiles SPIR-V to Vulkan. So with this unholy setup, we can actually compile Julia code to SPIR-V and then cross-compile it via Rustical and Zinc to any Vulkan API that supports SPIR-V compute shaders. Again, this makes it possible to run on an NVIDIA GPU via yet another way. But for example, it also makes it possible to run on Raspberry Pis because the Raspberry Pi 4 and 5, they actually come with a Broadcom GPU Vulkan driver. So with that driver and this cross-compilation setup, it is possible to run code on a Raspberry Pi. So let's demonstrate that in detail. I've built Rustical and created the JLL already, so you can actually import OpenCL, import Rustical, and if you then do a version info, you can see on my workstation that the NVIDIA GPU is listed twice. Once via the NVIDIA driver, which is a proprietary one, but that only supports OpenCL-C. It's also possible to use it through Vulkan by using Rustical and Zinc, and that now does support native compilation. And you can show that I can show that by the final expression, which does broadcast operation, which obviously is implemented natively in Julia, and here is being cross-compiled to a format that can run on the NVIDIA GPU. And the other example was using a Broadcom driver. This is on a Raspberry Pi 5, again, allowing us to compile Julia code for the Broadcom GPU in a Raspberry Pi 5. And basically, the only thing this requires is a sufficiently powerful Vulkan driver because it needs a handful of extensions, such as, again, the buffer device extension that allows the system to take device pointers, which is something we require to be able to represent all of Julia's structures on the GPU. And if you're interested in how this works, you can actually set an environment variable, the Zinc debug environment variable. Here I'm setting it to NIR and SPIR-V, which will show the intermediate NIR code, which is the new IR, as well as the output SPIR-V code. So first I'm showing the SPIR-V code that we generate using GPU compiler, and you can see here that the op capability is kernel, which means it is a compute kernel SPIR-V binary. Then it's going to get compiled from, translated from SPIR-V into Mesa's IR, and then finally Vulkan compute shaders come out of it and can get passed to the Vulkan API. And this all happens automatically by Rustical because Rustical is a full OpenCL implementation, so we don't actually have to use Vulkan.jl. This automatically goes through OpenCL. I'm mentioning here help wanted because the idea here is that these are proof of concepts. It does work, but it needs to be polished. So if anybody's interested in running Julia on any of these devices using these flows, the hard work has been done. The proof of concept is there, the JLL builds. Now we just need somebody to go through and fix all of the paper cuts and all of the small issues that are left to get the system to pass all of the tests. But for example, in the case of the Raspberry Pi, there's quite a bit of test failures. In the case of NVIDIA, almost all tests pass. So if you're interested in running OpenCL on an NVIDIA GPU, this is the way forward. The other way forward was to use SPIR-V to CLC, which is the source-to-source compiler going from SPIR-V IR back to OpenCLC. You can here see the generated kernel for, again, a simple vector addition. Again, proof of concept, works for the simple stuff, does not work for the complicated stuff. So if you're interested in targeting specific embedded devices that only support OpenCLC, the basics are out here. Get in touch, and we should make it possible to extend the JuliaGPU toolchain to way more devices using this. All right, a little faster than expected, but nonetheless, that was it for my talk. As a short summary, we've brought OpenCL.jl back from the dead. It's modernized and fully integrated with the whole GPU ecosystem now, allowing you to use it to program OpenCL GPUs in a modern way that integrates well with the rest of the Julia ecosystem. This allows it to target quite some new GPUs that weren't possible to program before because OpenCL is a fairly versatile toolkit, but ultimately the goal for us is to use this in combination with PoCL and take the kernel abstractions library to a next level by adding a proper CPU backend to it. Thanks.
Cool. We definitely have time for some questions. Just please put your hand up and wait for me to give you the microphone so that the question will appear on stream. If anybody has questions for the speaker. Awesome.
Awesome work, Tim. Perf questions. I know it's early times yet, but do you have data on, for instance, CUDA, or rather NVIDIA backend performance through OpenCL versus through CUDA, and natively written Julia with add threads or whatever versus an OpenCL kernel on the CPU? Do you have like any comparisons?
At this point in time, we don't have any proper performance results to show. I haven't even tested them when trying to do the funky cross-compilation to, say, an NVIDIA GPU or Raspberry Pi GPU. We have done some tests on the CPU, and it is, in certain cases, able to outperform even native threaded code on the CPU, because it also does auto-vectorization within the for loops that it generates. The only problem there is that we're actively working together with the PoCL team to make sure that Julia code is compiled correctly. So currently the parallel region detection codes that they have is not always properly able to deal with the code that Julia generates, specifically because of our heavy use of exceptions. That means you get aborts and unreachable code in heavy divergent parts of your parallel regions. And the auto-parallelizing compilers really do not like that. So we're still trying to figure out a way there, what the best way is to support the parallelizing compiler, which has a great performance, and to support it widely with Julia code. So once that's done, we can move on the next step and do some performance evaluation.
So we definitely have time for a couple more questions, so don't be shy.
I missed the start, so hopefully you didn't answer this already. But with the existing kernel abstraction CPU backend, you don't have to install anything. Like, you can just run it and test it. But with this new backend, you will be required to add a new package to actually use it, correct?
No, because we opted to not have it depend on OpenCL.jl itself. So we chose to pick the API wrappers and the JLLs that we need from OpenCL and add them as a default dependency to kernel abstractions. So when you'll install kernel abstractions, you'll see that it will additionally pull the PoCL, but it will be a full dependency of kernel abstractions. So you will not have to install any additional dependencies. It will still work out of the box. And in order to do that and not have people pay the price of having to precompile the whole OpenCL stack, we moved that code inside of kernel abstractions.
Okay, thanks.
Do we have any other questions for the speaker? Is there a question over there? Or, okay, someone was just stretching. We'll give people a second to think. It's hot in here, so. If not, let's thank Tim again for the great talk about OpenCL. And we'll come back at 2 p.m. So if you need to run to the washroom, Aaron, if you want to start setting up, Aaron's going to be our next speaker talking about trajectory bundles.